All right, let's move on to item number 21. In how many ways can a committee composed of 4 boys and 5 girls be chosen from a group of 7 boys and 10 girls? So take note when we speak about a committee here, order does not matter. So this one involves combination. With such, so out of the 7 boys, you will take 4 of them. So that's 7 combination 4. And applying the formula earlier, that's 7 factorial all over 7 minus 4 factorial, 4 factorial. And out of the 10 girls, you will be choosing 5 of them. So that's 10 combination 5, which simplifies to 10 factorial all over 10 minus 5 factorial times 5 factorial. And doing algebraic processes, 7C4 actually simplifies to 7 factorial all over 3 factorial, 4 factorial, or 35. Whereas 10C5 is 10 factorial over 5 factorial, 5 factorial, which is 252. And by the fundamental counting principle, we have to multiply them. Hence, there are 8,820 possibilities. I hope you got this. Okay, moving on to item number 22. Serena has found 5 foreign films and 4 local films she likes in a DVD shop. She is going to buy 4 of them. Find the number of combinations of buying at least 1 foreign film. So this means that it's either you buy 1 foreign, uh, 3 local, you could have 2 foreign, 2 local, and so on, right? So for this one, we have actually 4 possibilities. The first one is out of the 5 foreign, you will buy 1 of them. And out of the 4 local, you will buy 3 of them. So that's 5C1. And by virtue of the fundamental counting principle, I multiplied 5C1 with 4C3. The second case is uh, 2 foreign out of the 5 possible options and 2 local out of the 4 options. The next one is 5C3. That's 3 foreign, 1 local. Multiply them. And lastly, all foreign, so 4 foreign and non-local. And we will apply the combination formulas here, and by substitution and by simplification, 5C1 is 5, 4C3 is 4. This actually simplifies to 20. 5C2 is 10, 4C2 is 6, and 10 times 6 is 60. 5C3 is 10, 4C1 is 4. You have this. 5C4 is 5, and 4C0 is 1. That's why we have 5 times 1 here. And that's why, since you have 4 different cases now, take note, we apply the fundamental counting principles, the principle here by multiplying them. Here also to get 60, this one to get 40, and this one to get 5. And this time, since you have 4 different cases, then you now need to add them. Hence, there are 125 ways to do such. If you got 125, congratulations. All right, moving on to item number 23. The table below shows the number of outstanding students from Class Apple and Class Manzanas of a school in math. Mr. Solis plans to select 4 of them to join an inter-school math competition. Find the number of ways of choosing at least 2 boys. So what does this mean? So you could have 2 or more boys as long as you pick any 4 of them. You pick any 4 of them, you could have 2 boys, 3 boys, or 4 of them are all boys. So from this one, so you could see that in Apple has 6 boys and Manzanas has 4 boys. So therefore, there are a total of 10 boys. And Five girls are from class Apple, six are from class Manzanas, and this means there are 11 girls. So having at least two boys, so that's out of the 10 boys, you could choose two. And if you will choose two boys, since you will take four, it also implies that you will take two from the 11 girls. That's why 10C2 here is the number of ways for you to get the two out of the 10 boys, and here two out of the 11 girls. And by the fundamental counting principle, again, we have to multiply these two. This is the first case that you have two boys and two girls. The second case is if you have three boys and one girl. So you multiply them again due to the fundamental counting principle or based on that principle. And the last principle is four boys and no girl. That's why you have 10C4 times 11C0. Simplifying these, you have 45 times 55 plus 120 times 11 plus 210 times 1. Multiplying each would give you 2,475 plus, this is the number of ways for you to have two boys and two girls. 1,320 ways for you to have three boys and one girl, and 210 ways of having exactly four boys and no girl. And adding them all gives you 4,005. I hope you got this. And if you did, congratulations. 25. I mean 24. In how many ways can Jillian invite at least one of his seven friends to attend a party? So when you invite friends, again, order does not matter as long as they are present in that set. So this is again a combination problem. Try this out and let's see if you got this right. So you could invite meaning at least one, meaning you could invite a one, two, three, four, five, six, or all of the seven of them. And this means that you will add the values of 7C1, 7C2. 7C1 is inviting exactly one friend. Here, inviting exactly two friends, all the way until 7C7, wherein you invite all of them, right? So with such, by using the formula, and you could verify these on your own, this is actually equal to 7 plus 21 plus 35 plus 35 plus 21 plus 7 plus 1, which is equal to 127. So you have 127 ways of inviting at least one of those friends. But actually, there's another way for you to do this. And using the formula 2 raised to n minus 1. Take note, if you have n different elements, and if you will get at least one of them without any regard to order, then there are 2 raised to n subtracted by 1 number of ways. That's why our n here is 7 because you have 7 friends. And by applying the formula 2 raised to 7 minus 1, what is this 1? This is actually combination 0 because n combination, if n is a natural number, n combination 0 is equal to 1. So this is the number of ways that you will not get, that you will get nothing. That's only one way. That's why 2 raised to 7, which is 128, minus 1, it's equal to 127. So you see, we have two different approaches here, but we still arrive to the same correct answer. 25. I hope you got this. How many positive integers with 5 digits or less that have a digital sum of 9? When we say digital sum of 9 means that the sum of all of its digits is 9. For example, if you have the 5-digit number 40,113, 4 plus 0 plus 1 plus 1 plus 3 is equal to 9. So how many have a property that have 5 digits or less? Meaning it could have just 5 digits, 4 digits, 3 digits, 2 digits, or 1 digit, right? You may pause the video and try solving this first on your own. All right. Now, let's see if you got this. Let us represent each number accordingly with a number of dots and some plus symbols. For example, I'll just give a few examples. Let's say if I have this 5 digit number, 4, to get the digital sum, remember we add them. So 4 is represented by 4 dots, plus 0, no dot here, plus 1, that's why 1 dot, plus 1, 1 dot here, plus 3 dots here. Let's say I have, if it is a 4 digit number, it is already understood that the thousands place digit or the 10,000s place is 0, right? So let's say, take note, it could have less than 5 digits. So you could disregard the 0 if you wish, but if you could see, you could have 0 plus 3 dots plus 2 dots plus no dots. So there's no dot here in the middle plus 4 dots. If I have a 3 digit number and one of them is, uh, or I mean, sorry, if I have a 3 digit number, it's already understood that the 10,000s and thousands place digits are all 0. So you have 0, nothing, plus 0, so no dot, plus 3 dots, plus 3 dots, plus 3 dots, and so on. Take note, these are just some of them. But if you could observe, in any number that satisfies the condition, there are always 13 objects, 9 dots, and 4 pluses. Take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. So 9 dots, 4 pluses. In the second case here, 1 dots, 1, 2, 3, 4, 5, 6, 7, 8, 9 dots still. 1, 2, 3, 4, 4 pluses also. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9 dots, also 4 pluses. So in other words, in whatever we do or we choose here, there will be always be 13 objects, 9 dots, and 4 plus symbols. Hence, we could have 13C9 or pwede, or we could also have 13C4 because it's actually a theorem that NCR is equal to NC. For example, if you could see, I will add the 9 and the 4. If you add them, if it's equal to your n, which is 13, then surely they will be equal if we're talking about combination. That's why you could solve either 13C9 or 13C4. Both of them are the same. So if I have 13C9 first, if I have the 9 dots, so there are 4 objects left, which are all plus symbols. And that would be applying the combination formula, that's 13 factorial all over 13 minus 9 factorial, 9 factorial, times 4C4 is 4 factorial all over 4 minus 4 factorial, 4 factorial. You will get 715 times 1, which is 715. I hope you got this. There is another way of solving this, and that is just using the formula 13 factorial all over 9 factorial, 4 factorial. You can just do this directly, this one. You can just go to this one, stick to this one, because anyway, this will just be 1. Okay? I hope you got this. 26. You have 8 flowers and you intend to put them to 5 vases only. In how many ways can this be done? If each vase should contain at least 1 flower. So in this case, no vase should be empty. What do you think is the correct answer here? Okay? Let's solve. Let's see if you got this. So since each vase should have at least one flower, then we assume that you put one flower to each vase for now. And so 8 minus 5 gives you 3 flowers that may be placed in any vase. How come? Because by putting one to each vase, we are sure that no vase is empty and that the 3 flowers can be placed anywhere, and some vases could have more than one flower. So let's call these vases V1, V2, V3, V4, V5. Let's say the 3 could be placed either flower plus flower plus flower plus the remaining 2 have no flowers left. It's also possible that no flower here plus flower plus here vacant plus one flower here. It's also possible that the 2 flowers should be placed in vase 1 plus none plus none plus none plus the last one here and many more, right? But in any possibility, like if you go back here, how many Fs do you see? You could see 3 Fs and 4 plus symbols. In the second case, still 3 Fs and 4 plus symbols. In the last one, example I gave, there are still 3 Fs and 4 plus symbols. In other words, we are sure that we have to arrange 3 Fs and 4 plus symbols, and there are a total of 3 plus 4 or 7 objects. That's why it's 7C3 times 4C4. 7C3 is the number of ways for you to have your flowers, and 4C4. And if you have those 3, the remaining 4 slots will be for the 4 pluses. And by simplification, that's 7 factorial all over 4 factorial, 3 factorial, times 4 factorial all over 0 factorial 4 factorial, which is just 35 times 1 or 35. I hope you got this again. And if you did, congratulations. Or there is another way that's easier. You can just stick here. Remember, this could be an indistinct permutation problem, right? So that's 7 factorial all over the 4 factorial for the 4 pluses and 3 factorial for the 3 identical Fs. So that's another approach. All right. 27. There are 9 points in the square lattice as shown. How many triangles can be drawn that contains at least 3 of these lattice points? All right. What is your answer? What's your guess? Let's see if you got it right. So take note, to form a triangle, there are 9 points here, particularly lattice points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And if you choose any 3 points without restrictions, that would be 9 combination 3. And that's 9 factorial all over 9 minus 3 factorial, 3 factorial, which actually simplifies to 84. In other words, there are 84 ways for you to choose, for you to connect any 3 points. However, we have a problem here. There are 8 ways to choose 3 points that do not form a triangle since they are collinear. We have known for a fact that if you have 3 points that lie on the straight line, then they are not considered triangles. For example, here, horizontal, let's say this one, let's have the horizontal ones. These 3 are forming a straight line. So this is not a triangle. So 1, 2, 3. And the vertical lines, 4, 5, 6. The diagonals, 7, 8. That's why there are 8 ways for you to choose 3 points that do not form a triangle. And out of the 84, since there are 8 ways that don't form a triangle, since they are collinear, then by the complementary rule, we have to subtract them. Hence, there are 84 minus 8 or 76 triangles in all. All right. So you see, the complementary rule is also very important. 28. Andy plans to arrange 3 different mathematics, 2 different science, and 4 different English books by stacking them in a pile. What is the probability that all math books are together? Okay. So what's the chance? What are the chances that they are all together there? So if you have this, take note, if there are no restrictions, then these 9 books, how come 9 books? That's 3 plus 2 plus 4. That's 9 different books, could be arranged in 9 factorial ways in all. So that those are the total number of possibilities. And later on, this will serve as our denominator. However, if we have, let's say, we have here your 3 math, your 2 science, and your 5 English books. And if we have to make sure that all math books are together or are stacked, are together, I mean, so we have to place there or box them, and this will be considered as 1 slot. So how many slots do you see? We have 1, 2, 3, 4, 5, 6, 7. That's why there are 7 factorial ways. However, these 3 math books could still rearranged among themselves, could be rearranged or arranged in 3 factorial ways within this group. That's why there are 7 factorial times 3 factorial ways to arrange the book such that all math books are together. We multiplied the 3 factorial to 7 factorial because here order matters. So take note that if we are talking about classical probability, it's equal, the probability that all math books are together is equal to the total number of favorable outcomes, which is 7 factorial, 3 factorial, all over the total number of outcomes, which is 9 factorial. I expressed the 9 factorial as 9 times 8 times 7 factorial because I know that the 7 factorials will just divide it into 1. The 3 factorial is actually equal to 6. 9 times, so this will cancel out the 7 factorial. So 9 times 8 is 72. And 6 divided by 72 simplifies to 112. Hence, the probability that this happens is 1 over 12. Did you get this? If you do, be proud of yourself, and I hope that you understood the solution well. If not, I hope that it is a learning experience as well. 29. 5 fair coins are tossed at once. What is the probability that at least 3 heads come out? Now, meaning you could have 3 heads, you could have 4 heads, or all 5 heads. So here, by the fundamental counting principle, there are 5 slots, 1 for each coin, and each coin could have 2 results. So that's 2 times 2 times 2 times 2 times 2, or 2 to the 5th, or 32 possible outcomes in all. And this will be our denominator. But for you to have at least 3 heads, there are actually 3 cases. You could have 3 heads and 2 tails. That's 5C3. Out of the 5 coins, you will have 3 heads, and the remaining 2 will be tails. That's why 2C2. 5C3 is, this simplifies to 10 times 1 or 10. For the second case, you have 4 heads. Out of the 5, 4 heads, and the remaining coin will be tail. That's why 5C4, and the remaining 1 will be tail, so 1C1. And simplifying this gives 5 times 1 or 5 outcomes. If you have case 3, 5 heads and no tail, that's 5C5 times 0 combination 0. Be careful, 0 combination, 0 factorial is equal to 1. So 0C0 becomes 1 factorial over 0 factorial, 0 factorial. which is actually 1. So 5C5 is also equal to 1, and 1 times 1 is 1. Since you have three distinct or different cases, and by addition, there are 10 plus 5 plus 1, or 16 possibilities to have at least 3 heads. But knowing that there are 32 outcomes in all, the probability of having at least 3 heads is 16 over 32, which is 1/2. Okay, and we have one more. 5 students from SPSTE and 7 students from STBEP are being eyed as contestants for Sayawi. If the official entry of the school should have 6 members only, what is the probability that exactly 3 of them are from SPSTE? So if exactly 3 of them are from SPSTE, it follows therefore that 3 of them should come from STBEP, right? Now, from here, we will choose 6 out of a total of 5 plus 7 or 12 students. So therefore, if there are no restrictions, 12 combination 6, which is 924, is the total number of ways for you to choose any 6 of them. However, if you will choose 3 out of the 5 members of the STE, then the remaining 3 should come from the 7 STBEP people. So that's why you have 5C3 times 7C3 by virtue of the fundamental counting principle as well. That's why we multiply them. 5C3 simplifies to 10. 7 combination 3 simplifies to 35. And therefore, there are 350 ways to choose exactly 3 from SPSTE and 3 from STPEP. So out of the 924, 350 are favorable of having exactly 3 SPSTE students. And hence, you have 350 over 924. And therefore, this probability simplifies to 25 over 66. And if you got this right, great job. And this ends our review. I hope you learned something. And hopefully this will prepare you for your examinations. Thank you very much and a great day to one and all.